Dr. Greg Swain, working on developing a method for the electroanalytical detection of propranolol using flow injection analysis. So in my project, I sought to evaluate the ability of 3 different electrodes to sensitively, reproducibly, and stably detect concentrations of propranolol. These 3 different electrodes were first glassy carbon, second a boron-doped diamond thin film electrode, which I'll just be referring to as diamond, and nitrogen-incorporated tetrahedral amorphous carbon thin film electrodes, or just TAC. And these concentrations of propranolol in standard electrolytes and synthetic urine were detected using a technique known as flow injection analysis with amperometric detection. Essentially, flow injection analysis is an electrochemical-based method. It's extremely cheap, very fast, very easy and simple to understand. And essentially, sample or your analyte is injected into a continuous flowing stream of carrier solution, or your electrolyte. In the case of my project, I used 0.1 molar phosphate buffer with a pH of 7.2. So as your carrier solution is flowing through, you inject your analyte, or propranolol in this case, and it's incorporated into the flowing stream and eventually reaches the working electrode, which you can kind of see down there. As it passes across the surface of the working electrode, depending on the potential that you apply, either an oxidation or reduction reaction will occur. I'm applying extremely positive potentials, so an oxidation reaction occurs, meaning that the propranolol, when it comes in contact with the surface of the electrode, becomes oxidized. You know that electrons have charge, so this movement of charge in turn generates a current, which I can then detect. So in the diagram below, you see when the reaction occurs, a peak is generated in the graph, indicating an increase in current. So basically, current is directly proportional to the rate of the electron transfer. And consequently, if I were to increase or decrease the concentration of the propranolol, I would see a similar increase or decrease in the current. So some of you might ask, why should we bother studying flow injection analysis? If you know any other methods for the separation or detection of molecules, you might know like HPLC, high performance liquid chromatography, is much more efficient, it's much more accurate. You have differential pulse polarigraphy or a bunch of other methods. So why would we bother using flow injection if you have things that are so much more accurate? And the reason is because the people who want to use flow injection are working in the pharmaceutical industry. So most times pharmaceutical companies, they're hoping to test the quality or purity of their drugs, or maybe to non-invasively detect different pharmaceutical compounds or biomolecules in the human body or in urine. So they don't necessarily need that very, very high degree of accuracy that HPLC yields. Instead, they might look for flow injection analysis. It's extremely cheap, it's simple, so someone without an extensive scientific background would still be able to operate it. It's very fast because you have that continuous flowing stream, so there's no need to clean the clean. And it's very versatile. It can be made out of a variety of different materials. So because flow injection enables quick detection of multiple analytes with very, very high sensitivity, it's a good method, so we should study it. Basically, in lab, this is how the flow injection system is set up. Up there, you kind of see the diagram of how it works. You have a carrier solution pumped through a couple different machines, and then eventually it reaches the flow cell. And inside of the flow cell is where all of the reactions, all of that occurs. And then you have the potentiostat, which detects the current. So in the flow cell, it's in the bottom left corner. I actually use a 3-electrode flow cell. There's a reference electrode, which I use a silver-silver chloride electrode. And for that one, it's held at a constant and known potential against which all other measurements are made. The working electrode, which you can see down there, that's your glassy carbon or diamond or TAC electrode, and that's where the reaction takes place. And then you have a counter or auxiliary electrode, which is just the platinum wire. And in the flow cell, it comes in through the inlet, which is the green line in the picture on the right, and exits through the waistline, or the yellow. So it comes in contact with the working electrode, reactions happen, and it just exits the flow cell. Something else important to recognize is that the cell volume is always smaller than the injection volume, because you want to make sure that whatever you inject, you're taking up the full capacity of the flow cell. So that's important. Now on to what I'm actually trying to detect, propranolol. It's available commercially as propranolol hydrochloride, and that's what I'm actually using. Propranolol is an adrenergic non-selective beta antagonist that blocks the action of norepinephrine and epinephrine from binding to beta-1 and beta-2 adrenergic receptors. It's primarily used to treat hypertension, anxiety, and panic, and it's been listed on the World Health Organization's list of most essential medicines, so it's pretty important. Effective plasma levels are around 10 to 100 milligrams per milliliter, and it reaches peak plasma levels 1 to 3 hours after ingestion. And after this, it's excreted from the body in urine, primarily in its metabolite form. And what I'm actually examining is the oxidation of propranolol when it passes across the surface of the electrode. You can kind of see it down there, so it loses 2 electrons. And that's what generates the current. So you might recall me mentioning I'm testing 3 different electrodes. The first, all 3 of them are carbon electrodes, which are good for their renewable surface. So the first one is glassy carbon. Glassy carbon has been in use for a very long time. There's an extensive body of research regarding its properties. In terms of its structure and characteristics, it combines the glassy and ceramic properties of non-graphitizing carbon with graphite. It has an sp2 hybridization structure, and you can kind of see from the picture on the right, it has graphitic nanoribbons kind of moving around everywhere, and this contributes to its anisotropic microstructure. So basically, it's disordered, but it's disordered everywhere. So theoretically, if you had a first layer, you took the first layer off, the second layer should still be the same microstructure. And it's this property that allows us to polish it. After using glassy carbon for a couple of times, the surface might become deactivated, so you have to polish it to remove any surface contaminants or oxidized compounds, and you remove some of the carbon to reactivate the surface. The thing about polishing is that it takes a really long time. You sit down for an hour and you make figure eights on the polishing pad, and it's very tedious, and pharmaceutical industries, they might not want to have to spend that time polishing. It's an inefficient use of their time. And in addition to that, since you're removing layers of carbon, you would have to reevaluate the quality of the electrode. So it's pretty inefficient to use. And not only to mention that, at higher and more positive potentials, some of the microstructure of the glassy carbon surface might change, so it's not optimal for detection. So instead of glassy carbon, we have something known as boron-doped diamond. Boron-doped diamond, it's newer than glassy carbon, but there's still a very large body of research on it. It contains sp3 hybridized carbon bonding and exhibits properties of very high stability and chemical inertness, so that's very good. Diboron is incorporated into the diamond films during growth, and this is known as boron doping. And essentially, doping increases electrical conductivity, so the greater the level of doping, the greater the level of electrical conductivity. The diamond thin films are grown on silicon substrates, and because it's a thin film, it doesn't require any polishing, so that's good. And you probably have a pretty difficult time trying to polish a diamond. So that's your diamond electrode. The third type that I'm trying to test is nitrogen-incorporated tetrahedral amorphous carbon thin film electrodes, or just TAC. TAC is pretty new. It is a combination of sp2 and sp3 bonded carbon. Nitrogen impurities are added during growth, and theoretically, TAC should share many of the same properties of diamond and perform about just as well. But the thing about TAC is that it's much more cost-effective and versatile than diamond is. Diamond is really expensive. TAC, not so much. And in addition to this, diamond thin films need to be grown in temperatures ranging from 600 to 800 degrees Celsius, and that's extremely high. TAC can be grown at room temperature, which means a much wider variety of substrates can be used for growth. So that's basically how my experiment is set up. But in order to evaluate which method is better, I need to have some figures, these detection figures of merit. So I run 3 different experiments, and I ask myself these questions each time. The first experiment I run is known as a hydrodynamic voltammetry experiment, and what are the optimum conditions for detection? And in this experiment, I try to find what the optimal potential is for detection for experiments later on. After that, I run a short-term reproducibility experiment. Reproducibility and repeatability are 2 of the most important characteristics any analytical method can possess. You want to make sure you can generate the data stably and consistently. So that gives me some insight in regards to that. And the last experiment I run is known as the calibration curve determination experiment, which tells me how well the method can actually detect propranolol in terms of distinguishing between signal and noise and how wide of a range it can actually detect. So the first experiment, hydrodynamic voltammetry. So I injected 500 micromolar propranolol in potential range, you can kind of see at the bottom of the axis. And for glassy carbon, diamond, and TAC, the optimum potentials are at 1250, 1350, and 1325 millivolts, which you can kind of see from the arrows. So hydrodynamic voltammograms usually exhibit something of a sigmoidally shaped curve. So it starts out low, kind of increases, and then plateaus towards the end. And when it starts to plateau, we know that that's where propranolol oxidation is maximized. But you might ask, in these graphs, it kind of plateaus and it shoots right back upwards. And this large increase in current is probably due to the fact that other things inside of my carrier solution, maybe water, is getting oxidized. So that's why the current is increasing so fast towards the end. After running the hydrodynamic voltammetry, I know what potential to run the rest of my experiments at. So the next one I do is a short-term reproducibility experiment. I make injections of 5 micromolar propranolol. I make 25 injections every 60 seconds. And for this, you kind of see glassy carbon, diamond, and tack. They're all pretty reproducible, which is very good. The percent RSD is all under 10%. So we know that this method is pretty reproducible. We can probably move on to the next step. And that's our calibration curve determination. So from the calibration curve, we can gain a large variety of figures of merit. The first one is sensitivity. Sensitivity is the ability of an analytical method to distinguish between the analytical signal and the background noise. So the sensitivity is just the slope of the calibration curve. You might notice that for a diamond and tack, the trend line, the slopes of the trend line are much, much greater, and this shows greater sensitivity, which is good. In addition to that, you have something known as the linear dynamic range, which is the useful range of an analytical method. And you can kind of notice towards the end, the brownish curves are starting to slope off, and that's where it's reached the limit of linearity. So beyond that, it's not very good at detecting it because the slope is no longer linear. And it's not immediately obvious from this graph, but glassy carbon has a much higher detection limit than both diamond and tack. So diamond and tack can detect a wider range. This is just a summary of the detection figures of merit. These are just some of the numbers. You might notice that the detection limit for diamond and tack are much lower than for glassy carbon. That's good. But numbers, you can't really tell much information. What do these numbers really mean? In terms of diamond and tack versus glassy carbon, diamond and tack both have a lower detection limit and a much wider linear dynamic range. The values are more reproducible, indicating that there's less fouling or surface absorption on the electrode. And basically, fouling is when analyte accumulates on the surface of the electrode, preventing future injections the future reactions from occurring. Diamond and tack are also more sensitive, so it's better at distinguishing between signal and noise. So clearly, diamond and tack are better than glassy carbon, but the line between diamond and tack isn't necessarily as clear. They have similar detection potentials, only 25 millivolts apart, and depending on the electrode that you do throughout the day or the carrier solution, that might change a little bit. Diamond has a much lower detection limit and a wider linear dynamic range, but tack is more reproducible and sensitive. So, in a broader sense, flow injection analysis with amperometric detection is a very viable method for the detection of propranolol. It's good. In terms of your electrodes, diamond and tack obviously outperform glassy carbon, and while diamond and tack perform similarly, tack is probably preferred for its cost effectiveness and versatility. So tack wins. For future directions, if I have time, you could further optimize the method for detection, maybe by testing different electrodes, changing the surface chemistry, using different gaskets. You could also test other pharmaceutical or biological compounds that are often taken with propranolol, such as hydrochlorothiazide, or biomolecules like norepinephrine and epinephrine, and maybe simultaneous detection. You can also replicate commercial conditions by collecting and testing real urine samples like someone in the pharmaceutical industry might actually do. So acknowledgements. I just want to thank Dr. Swain for being fantastic over these past 7 weeks and dealing with all of my annoying questions. Denisha and Romana, who showed me how to work the flow injection system and were always there whenever I needed assistance or support. Dr. Richmond for picking me to come here, and all of you guys for the best summer of my life.
Questions for Joy?
Okay, so you said that propranolol is really important because it's like a widely used drug. But why would you want to test it in somebody's urine?
In case when it's excreted, or maybe that's how pharmaceutical industries might get the propranolol inside of urine samples. So we're just trying to replicate it as closely as possible.
Can you repeat to me how you determine the detection potential again? Because in your surveying experiment, it looks to me all the graphs are going up. It's not like there's a peak. So, right, this one.
This one?
So where exactly, how do you, this looks to me they're all going up in trend. So how do you come to conclusions that that potential was the optimal voltage that you would choose for your detection?
So hydrodynamic voltammograms are usually supposed to be sigmoidally shaped. So once it starts to plateau, use a laser pointer. So once it starts to plateau, which is like around there, you can kind of see it
Wow.
start to, the slope kind of decreases, and then it starts to shoot up sharply again, and you can kind of see right there and right there. So
Okay.
you know, there's like other things getting oxidized, like those extremely positive potentials, but once you can kind of see it plateauing, that's how we know that's where oxidation is maximized.
I can see a little bit, okay. But because if you factor it into error bar, it looks to me just go up in trend. But I can see a little bit.
Any other questions?
Like kind of following up the question, like when you see the diamond graph there, it looks like it could be considered plateauing, like two dots to the left of where you have the arrow. So is it exactly where it first happens, or like how do you differentiate between the two? Because like it almost looks like it plateaus.
That's exactly.
Oh, at 1250.
Yeah. Like it seems a little bit larger.
Kind of. It's just like where you can best see where the current is starting to plateau a little bit, and when you look at the slope of it and how much is decreasing in relation to the background current, you kind of just take a value.
Okay, yeah. Like if you looked at that something, it would be a lot. Okay, yeah, that makes sense. Thank you.
So you said that TAC was sort of a mixture of sp3 and sp2 carbon. Is it? Do you see it as being sort of like the carbon, the amorphous carbon structure? I mean, I guess you said it was something you could form at room temperature, or I mean at modest temperatures, 25 to 100. Yeah. So how do you make it?
I didn't actually grow these. I'm not exactly sure, but I will get back to you.
Okay. Okay, yeah, I'm just sort of curious. I mean, it's the carbon-carbon bonds are pretty strong things, and it's so how they get formed at such modest conditions. It's a very intriguing thing to know.
Did you do testing with the synthetic urine with all three of the electrode types?
Yeah, actually, so the carrier solution I used is phosphate buffer, but the propranolol solutions were diluted with synthetic urine.
Did you-
That's how you would do those.
Okay. Did you see any fouling in any of them with the use of the synthetic urine? Like,
Yeah. For the short-term reproducibility experiment, this is actually at a lower concentration of 5 micromolar. When you increase the concentration more, fouling does occur. So at the beginning, you might have higher current, and then it decreases over time. And that happens at slightly higher concentrations.
and did you see more fouling in the glassy carbon than the